Welcome back. In this video, we are going to see the second way of representing a binary tree, which is a linked representation. In the previous video, we have seen how do we represent a binary tree using an array. Today, in this video, we are going to see the second way of representing a binary tree, so which is going to be a linked representation. So let us see what it is. So before we see what actual linked representation, let us see what are the drawback in array representation. So what happened with the array representation? So much space got wasted. That is the first thing. And the second was it was difficult to insert or delete an element at the middle of a tree. We could do it, but it was time consuming. So many changes, movements should be done for this. So these two drawbacks of representing a binary tree in the form of an array can be overcome using a linked representation. Let us see what it is. So to represent a node in the form of a list, as you know, every node is divided into three parts, which are the left child, which contains the address of left subtree. There is a right child, which contains the address of the right subtree, and data. So data is the actual information, the actual data. So every node in a given tree will be divided into three parts to represent the node in the form of a linked list. So let us see what is the actual code looks like. So obviously you have to take a pointer for this, a structure for this. So you have taken a pointer called tree pointer, as you could see, and we have taken a structure called type def. So type defined structure we are going to take, and with three members. The first member is the data, which is going to store the actual information, and you can find two tree pointers. One is for the left subtree, we have taken it as left child, and other one is for the right child. And please look at what are its type. Its types are tree pointers. And we have done with this C code. So look at, we have taken a type defined structure, or you can say that we have created our own type called node, and for nodes we have a pointer called tree pointer, and we have created two variables of tree pointer. One is the left child and other one is the right child. So we have created our own structure to have a three pointers, and the pointers are left and right child. So this is what the actual pictorial representation. As you could see on the diagram, every node is divided into three parts. This is what the actual thing, and the middle one is the data part. Left child have its own separate segment, and right child is going to have its own separate segment. So let us see a tree, and later let us see how we can represent this actual tree in the form of a list, a linked list. Okay, so you could see two diagrams on the screen. The first one is a skewed binary tree. That means it's a tree only with left subtree, right subtree is missing. And second one is a complete binary tree. We have seen what is a complete binary tree. Again, basically a complete binary tree is a tree where you can find all the levels of the complete nodes other than the last level. So let us see how we can represent this. So these are the ways we are going to represent the skewed tree and the complete tree. So this is for the first diagram. So the first node A is divided into three parts and which does not have any right child, so we have put it as null. And for A there is a left child B, so we have got a pointer from left of A node to the next node, which is B. Again B, there is no right child, so this is null. B has got a left child, which is C. C does not have any right child, so this is again null. Again C has got a left child, which is D, and D does not have any right child. Again same for E, which does not have a right child. So we have successfully represented a binary tree, which is a skewed binary tree, into a linked representation. So let us see the second one, where you could find a tree which is complete binary tree, and as usual we have to start from the first node. The first node is the root node, which is divided into three parts. The left is for the left subtree and the right is for the right subtree. The left subtree, you can find B as the root, and B has got two nodes D and E. So we have taken B with two children D and E, and E has not got any child, so we have put it as null. Same way we'll go to D, whereas D has got two children, one is H, other one is I. So we have done with the left subtree of A. Next we should move on to the right subtree, where you can find a left subtree rooted at C. So there is a right child for A rooted at C, and C has got two children, one is F and other one is G. You could see there, and both does not have any right and left children, so you can find there is a null value for F and G. So we have successfully completed a normal binary tree, which can be of any kind, which can be complete binary tree, or which can be left or right skewed binary tree, which doesn't matter. All these kind of trees can be converted into a linked representation. And please do understand what are the advantages of representing a tree in the form of linked representation. So there are two advantages, as I told you. One is you can insert and delete, or insertion or deletion can happen anywhere in the list, because insertion and deletion we have studied in the previous chapters, which can be done easily. Second thing is, if you take an array representation, if the tree is a kind of skewed tree, like left or right skewed binary trees, which is going to waste almost half of the space. But when you convert this kind of trees in the form of list, we are not going to waste any space. So these are the two advantages of representing a tree in the form of a linked list.